In the previous video, I combined this video terminal and this high-speed reader punch onto a single serial port so that it looked like a teletype to an early microcomputer. And this allowed me to run the very first software that ran on early microcomputers that required a teletype as the console and the mass storage device. Now, if I were to run this at 110 baud like a teletype, it would have worked fine on any of the early computers or early software. However, the last thing you want to do with a nice high-speed terminal and reader punch is run it at 110 baud. I wanted to run it at 9600 baud. And as we saw in the video, we then ran into throughput problems. For example, when the computer was sending data to the punch at a full 9600 baud, it's faster than the punch could handle, even though it's a very high-speed punch. And similarly, I can't even say that. Likewise, there was a opposite problem when the reader on this is so fast it was actually faster than the computer could handle in some cases. Binary files in general were not an issue, but when BASIC was trying to load a source file, it could get overrun by this. And so we had to use handshaking and other tricks in that video in order to get a couple of very specific examples that were demonstrated working. One was on a Southwest Technical 6800 computer, and the other was running BASIC on an Altair 8800. And those were very specific solutions. If I changed anything about those, different hardware, different serial boards, different computer, different software, even a different version of BASIC of the same brand. In other words, if I went from Altair BASIC 3.2 to 4.0, I would have had to change some of the software and the patches we made to make it work. So it was not a universal or general purpose solution. And what I really want is a general purpose solution that would have worked with any of the early computers, no matter what software was being run. And that's what we're going to look at in the video today. A teletype communicates with the host computer serially at 110 baud. That's just 10 characters per second. That in turn is the actual throughput rate of the printer and punch on the teletype. So what that means is that the host computer can't possibly overrun the printer or punch on the teletype. So there's no need for any sort of hardware or software handshaking provision in the computer, at least not to support a teletype. Coming from the teletype back to the host from the reader, again, 10 characters per second, which is very slow, and all the old software could keep up with that. So there was no need for handshaking on the input side either. So what that makes clear is that my general purpose solution cannot assume that the computer or software has any option or provision for handshaking to throttle things. So it quickly becomes clear that I'm going to need something more intelligent in the middle between these devices and the computer than that simple Y adapter board I made in the last video. It's going to have to be some sort of intelligent device that can buffer characters as fast as they come from the host and then hand them out slowly to the punch at a rate that the punch can handle. Likewise, it has to be able to accept characters just as fast as they come from the reader and then hand them out at a rate that the host can handle them. Now, as a modern day hobbyist, I could easily do that on a Raspberry Pi or similar device. But as you've seen in my videos, I like to do things like a person would have done back in the day. So I'm actually going to use an Altair 8800 as the bridge computer. This is not the actual host computer. This is going to be the bridge computer that's in between. And I'll stick it underneath this shelf when I actually use the computer as sort of a black box. I'll have it boot off of, not boot, but run from EEPROMs, no console or anything like that. It'll be basically a black box. It'll be a bridge for me. Now you might think, who's going to have a spare Altair laying around back in the day? But by the time you could actually have done this, by the time this video terminal and a punch reader like this was available in the early 80s, Altair would have been out of production for 4 or 5 years. And you were using a faster Z80 machine running CPM with disk drives, or maybe even one of those new IBM PCs. So these computers were sitting on shelves collecting dust, being given away or sold at pretty cheap prices. You probably had one of your own, quite potentially, if you got started in the computer business or running microcomputers early. So yeah, it would not be that unlikely to have a spare one laying around, and it can do this job just fine. If we look inside, I've got 2 of Altair's 88 2SIO boards. Here's one over here, and here's one here. Each of these has 2 serial ports on it, so I've got a total of 4 serial ports here. So the 4th port right here is going to go to my reader punch. The 3rd port, which is right here, is going to go to the terminal. The 2nd port is going to the host computer. And then the 1st port on the 2SIO board, I'm reserving that as the console for this computer itself. Normally I won't need that, but if I ever had to work on or update this computer, that would be my console attachment, and I don't have to worry about disconnecting all the other cables. All right, I then have the CPU board that belongs in here. And then finally, I've got a 64K RAM board in here, which came out in 1980, so this would have been available in the time. This is a CompuPro RAM 17. It uses 2K static RAMs, which are pin compatible with 2716 EEPROMs. So it comes in handy is that you can put an EEPROM in just one of these slots. Let's see if I can find that down here. So here's the EEPROM down here, right there with a label on it. Just taking one of the RAM sockets. And so that's where I've put the PROM that handles that contains the code for this bridge computer. All right, so what does that code need to do? Well, we already gave you the quick overview. It has to buffer data coming in from the host. I have a 16K circular buffer I use for that. And then it has to buffer data coming in from the reader. I have a separate 16K buffer for that. And then it has to hand it out at a rate that the punch can handle or that the host computer can handle. And that will vary depending on the equipment you have and what software you're running and what computer it's on. So in order to allow you the ability to select that information on the fly, I'm going to use the sense switches on the computer to do that. So the lower 3 sense switches are used to determine the rate at which you can send data to the punch. If you set it to 1, it'll send it out at 10 characters per second. That's really slow, like a teletype. 2 is 20 characters, 3 is 30 characters, 4, 5, 6, up to 7, which is 70 characters per second. Now, if you have it on 0, there's no delay at all. And this would be if you used a reader that had a handshake line, like we saw in the previous video. It sends it out at full speed, but the handshake line determines whether or not the punch is accepting more. But if you don't have a handshake line on your serial punch, this will allow you to adjust the rate that it goes out. All right, the next 3 switches are used for the opposite direction. This is the reader going to the host computer. And as we saw, we need a delay after a carriage return. We know we need this for BASIC. I can tell you the editors and assemblers need this as well. And those are the most common packages in the beginning. So what we have here is similar to what we did before. 1 is 100 millisecond delay, 2 is 200 milliseconds, 3 is 300 milliseconds, which covers pretty much anything under BASIC. If you have something else that's very slow, you can go to 4, 5, or 6, or even 700 millisecond delay. Now, one thing we didn't cover last week is because BASIC could keep up with 9600 baud receiving characters in the line, it just needed the delay at the end. But some of the software actually can't keep up at 9600 baud, even queuing the characters for the line. So we need to slow down reception on a character by character BASIC in some cases, character by character basis in some situations. So these top 2 determine the character rate. 0 is full speed, 1 is half speed, 2 is 4 speed, and 3 is 1/8 speed. And we can change these on the fly because, like we'll see, we can go full speed loading a binary, but then we need to turn around and go to something else if we're loading a source, or possibly even something else when we're loading a binary within MIT's programming system, for example. We'll see that as well. So that's how this will work. So let's go ahead and take a look at the software now. All right, let's go ahead and take a look at the software that runs in the bridge computer. Here we see equates for the serial ports. We have the computer or the host serial port here, the terminal serial port, and finally the reader punch serial port. This console serial port is not used when we're running it in the bridge mode, when it's just a little black box running from EEPROM. However, I'm going to use the UART that was originally the console on this computer as a hardware timer to help pace the data as it gets transmitted to the computer and out to the punch. We'll see that in just a minute. All right, this program is orged up here at F1000. That's so it can run easily from EEPROM. Here we initialize all the serial ports, and then we fall into the main loop. So the first thing we do is go ahead and receive data and queue it for output later. So here we look to see if anything's come in from the computer, and if so, it calls this routine to go ahead and put it into a large queue for later transmission out to the terminal and to the punch. Here we look to see if anything came from the terminal. If so, it gets put into a different queue for later output back to the host computer. Likewise, we look for anything from the reader, and it gets put into the same queue as the terminal would dump it, because it's going to go to the host computer later as well. And that's it for receive. Very straightforward. Now after that, we have to then look at what transmissions do we have from these queues. And that's where it gets a bit more complicated, because this is where we have to worry about all the timing like we might set on those front panel sense switches. So here to do that timing, I'm using the unused console serial port to give me a 1-character tick time at which every action will be carried out, and I can keep timers. So here you can see I look at that console port and to see if I can send another character. If not, I just go back up into this receive loop. But when each time a character time has elapsed, at 9600 baud, for example, that'll be 960 times a second, I will fall out of this loop. I go ahead and just stuff another character in there. It doesn't matter. It's not going to any device because nothing's hooked up. But I'm getting a character interrupt at 960 times a second, basically in sync with the 9600 baud that everybody else is coming in and going out at. So if I have a character interrupt, then I come down here and I take a look at the 2 timers that I'm using. I have a timer for the computer output, and I have a timer here for the punch output. Computer output is in BC, that's a 16-bit value, and the punch timer is here in DE, that's also a 16-bit timer. So if that timer is already 0, meaning I didn't have a delay or the delay's expired, then I go ahead and see if there's any data descended. If not, then I go ahead and check the punch. If it's also exact same law, same rules. If it's 0, meaning there was no timeout active or it's already reached 0, then we go to check to see if there's anything to send to the punch. So those two are basically work the exact same way. So let's say the counter for the computer is 0. Let's go see if there's something to send. So the first thing it does is make sure that the UART's ready to accept a character. If not, it just exits. Then it looks to see if there's anything in the output buffer by comparing the insert and remove pointers. If not, it just goes back and continues. Now, if there is something, well, then it pulls it out and goes ahead and stuffs it into the UART right there. So then we just did our transmission, and then increments the remove pointer and wraps it for entry the next time. So now at this point, we want to decide, is there a delay for the next character? So that's what we're looking at here. So first thing we look at is, in the case of going to the computer, we're looking for the after carriage return delay. So if the character is a carriage return, then we come down here, we read from the sent switch, align it up, and then look up in a table that has all the delays based on what we have on the sent switches, and then moves that into BC. That's what we do right here in order to determine the next delay value. If it's not a carriage return, then we could have a delay after every character, and that's where I'm reading the front panel, the far left 2 switches. Here I get those by themselves, look in the character delay table, and move that into C and B. Now that's just a 1-byte value, so I just force the upper byte to be 0. And of course, we're going to do the exact same kind of thing here with the punch. Come down here to the bottom, you can see the tables. Here's the character delay table for the 4 possible settings. Here's the delay after carriage return for the 8 possible settings, and here's the delay after each punch character to give us the various rates of 0 all the way up through 70 characters per second. And that's it. The rest of the computer is basically just buffer space to handle the transmit buffers out to the computer and out to the host. So let's go ahead and do a demo now. For the demonstration, I'm going to run the assembler editor package that MIT's made available for this Altair 680 computer. This is a 6800 based computer, not an 8080 computer like the Altair 8800 is. The assembler editor package required a teletype as the operator console. It was used to load and save the programs, the sources you were working on, as well as the actual S-record binary that you might have punched to execute the program later. The teletype we're using, of course, is going to be this Glass Teletype that we've been using. And these devices are combined into a single serial port that can be throttled for the right speed for the computer using the bridge computer we made out of that Altair 8800. Now, the bridge computer just runs from EEPROM. I examined F1000 and hit run, and it's running. No console, it's just a black box other than the front panel switches that we'll be using. All right, so let's go ahead and get this party started. Go ahead and turn on the computer. Halt, reset, run. And that gives us our command prompt here on the terminal. That comes from the monitor that's running inside the 680. The command to load from paper tape is L. It's going to load an S record tape from the teletype. In this case, we have that S record tape. That's a ASCII hex version made by Motorola, like Intel hex. There's the program. It's a very large tape. It takes about 33.5 minutes to load on a teletype. Here we're going to get it done in 27 seconds, which is a great improvement. Now the S-record load process on this can go at full speed. So when it comes to any throttling, I don't need any. So I have these all set to 0 so that everything goes through at full speed, no change at all from as if it was just a direct connection. All right, so I got the load already started. Let me just go ahead and hit read on this paper tape and get it going. All right, so that's taken off pretty good. It's going to make a big old pile on the floor. As soon as it's done, I'll do a video cut so that I don't step on it and crimp the paper tape. And when that's done, we'll be back to a prompt here. The nulls at the end of the tape will generate a bunch of extra dot prompts. That's pretty normal, loading a paper tape, even from Teletype. All right, that's about to finish. You see that roll's got a good coast going on it there. All right, and there's our screen full of returns. But you can see that we're up and running. Here's the memory command, ready to go. All right, let me do a video cut, and I'm going to pick this pile of tape up off the floor so that I can continue without stepping on all that. All right, all cleaned up. Let's get up here to the console and start the assembler editor package. Jump to 0107 is the starting address. Does a little bit of initialization here, then it'll pop up into the editor. And before we can really do anything, we need to go tell the editor and assembler what the memory limits it has to work with are. You do that back in the monitor, so we'll do an escape to the monitor and modify those locations, which are 00D4. I'm going to set it to 4FFF, so that means everything above 5,000 is ours, and this is telling the editor and assembler to stay below 5,000 hex. Let me jump back into the editor assembler, and now we're sitting in the editor. Now the editor does not use carriage returns to terminate a command, it uses escape. You push escape twice, it's like hitting return. So if I wanted to display 99 lines of the edit buffer, I'd type 99T and hit escape twice, and basically we have an empty buffer. So at this point, you would like to load the source code tape that you saved the day before, let's say, of the program you were working on, and resume your work. And to load that, you use the A command, which is append, and hit escape twice. It now expects the source code tape to come in from the teletype. And I have that tape loaded in right here, ready to go. However, the append command cannot handle the full 960 characters per second of 9600 baud. It needs it to be about half that speed, and it needs a delay after every character turn. So I'm not sure if we can see my switches over here, but to have the incoming rate, it's these upper two switches. 01 means comes in at half speed. The next three determine how much time after a carriage return. 0001 or 001 is 100 milliseconds after each carriage return. So that'll give us the throttling we need. So now we can go ahead and hit run. Read on the paper tape, and that comes in. And when that finishes, you'll see we don't have our prompt back here yet. I don't know if you can see it, but if you look closely at these lights, they're flickering. I can see them, but it doesn't video well. But when those stop flickering, it's done. There, it just finished. So now if I come in here, we're back to our prompt. So by using that delay, yeah, the tape finished, but you can see it was a while before the data actually all made it to the computer. So now we can look at the whole buffer, and there's our program. Let me just make sure those first few lines look right. Yep, everything looks good. So now you would use this editor and make any little changes you needed. Then you'd want to go to the assembler and see if it worked. So you go to the assembler with the G command, and you run the two passes of the assembler. There's the first pass. Here's the second pass with a listing. And it shows you what your program looks like. You can see I have it running at 5,000. It started at 5,000, and now we're up to 507C. All right, so that's in memory now. We can test it. So let's go out to the monitor and jump to that 5,000 address. And here's our program. Enter a message. How many times? Let's repeat it 6 times. Okay, so the program works. So let's jump back into the editor. So now at this point, you'd want to maybe punch a tape of that so that next time you can just load this little S-record tape and run your program. So let's go ahead and assemble that. Again, there's the first pass. And instead of doing a 2L, we're going to do a 2T this time, which means punch to tape. However, we have to make sure that the output of this does not overrun our punch. Normally this would go to a teletype, which is locked in at 10 characters per second, but we have to tell it to slow it down. Now, one way, like we demonstrated in the previous video, is with handshake. But this bridge computer we make can also do it based on a character per second rate, like we talked about. So let's assume I don't have handshake on this punch and that it's a 50 character per second punch. So to do that, I'm going to set the, I don't have to really reset the input ones, but I'm going to. We're going to set these last 3 switches to 5, meaning 50 characters per second. So that will throttle the output to just 50 characters per second, and the punch should be fine. So I'm going to hit return here now. Well, let me turn on the punch. And hit return. And you can see it's coming out slower on the screen, and the punch is going at 50 characters per second, just like we needed. All right, simple as that. Let me eject the tape here. All right, and so now we have our program in S-record format ready to load just straight from the monitor. Don't even have to go into the assembler. You can just turn on your computer and load this tape now. All right, and so then at that point you might go back to the editor. Oh, you see we got it throttled by that output. Let me turn that off. So now it'll be at full speed again. All right, and so what you might want to do now is say, yeah, I like that program. Let me go ahead and punch this to tape. And that would be with the E command, which would then punch this to the tape. Now, I don't want to bother wasting tape because I've got running out of that good black tape that I have. But for example, you would set this to 50 characters per second. Probably never have turned it off for that matter. And then you do the E command. And here you can see it's coming out at that 50 characters per second like the punch actually needs. All right, so this is not really a demo of the assembler editor package. It was more a demo to show you how that bridge computer worked and made this terminal and this punch work as a Glass Teletype that's 100% compatible. No matter what the computer is, no matter what the software is, you can always throttle input and output as needed to handle whatever the computer and the software required without having to modify any of the original content like we did in the previous video. Now, I also did this with a Raspberry Pi, and frankly, it was easier to implement on that Altair than it was on the Raspberry Pi. It's much easier to access low-level functions and do the low-level timing on these old computers than trying to do it, coax a Linux operating system to do the delays I want and do multitasking like I needed. But anyway, so that does it for this video. It was really not that practical. However, I actually have used this bridge computer several times here lately, running other paper tape software on some old computers to do a test for some other people. So it actually has come in kind of handy, but it's probably not a practical project for somebody back in the day because you'd have been on to using floppy disk drives and IBM PCs and hard drives and all sorts of things that were amazing and new, and who wanted to mess with paper tape anymore, even if it was faster. All right, well, that's it for this one.